Good morning, good afternoon, good evening, everyone. My name is Junyoung Park. I'm a PhD candidate at the University of Texas at Austin. And it's a great honor to present my PhD studies to everyone using this Zoom virtual way. And so today my topic is occupant-centric building control, balancing occupant comfort and energy efficiency. So to begin with, my whole dissertation starting from this simple sentence: buildings don't use energy, people do. So we all agree these days, occupant behavior is the most important factor to understand the building energy consumption and tackling the problem related to building energy saving as well. At the same time, people spend majority of their time indoors, especially during this COVID situation these days as well. So we have to maintain comfortable environment for people, which is directly related to their health and productivity level. But in fact, that's not always true. So this is a photo of my research assistantship at Carnegie Mellon University. So I travel around the US government building and using this IAQ sensing and interviewing people and evaluating their satisfaction on building. No matter which building they are, what I learned is they always complaining about their building systems and their indoor environment quality. And that's absolutely true from other POE studies like industry standards or technological point of view. The main reason is that humans are not in the control loop. Sometimes they deactivate the sensing system or the sensors are located in the wrong way. But one example here is they use the static set points for everyone, even though everyone has different preferences level. So my PhD dissertation is try to review the articles why this kind of problem happened. So I review the research articles from human behavior, comfort, and smart building control research during my first year of PhD. Individually, both human behavior, comfort, and smart building control research shows huge developments, especially after 2010. There are a lot of numerous papers are published out there. So if there is a knowledge transfer between the two, then there's no such problems that I identified before. So I tried to analyze the relationship between those two fields using text mining technique. So each dot here represents how people use or how researchers use those scientific keywords in their scientific article. And the distance between the two bubble dots represents how the two keywords are co-occurred in the same document. Obviously, the keywords related to human comfort on the red side is far away from the keyword from smart building and building control research. That means they're not co-occurred in the same scientific article documents. And that also means the researchers from smart building field, including me, and we are predominantly focusing on energy efficiency rather than the thermal comfort or human comfort considerations. So my PhD dissertation was try to link those two fields using some keywords below. And these keywords are kind of hint me how can I tackle this problem, and they are popped up in this bubble diagram as well. So they are context-wise occupant adaptive behavior or indoor environment quality. And methodologically speaking, they are machine learning, intelligent controls, and environmental sensing. So prime example of this agent, OCC agent, is occupant-centric building control, which is actively studied in IAEBC, NX79. And under this paradigm shift in building control, OCC agent acquiring the data from occupants using indoor environment or human building interaction devices and updating the building control set point for building systems to provide a comfort. And the main objective here is balancing occupant comfort and energy efficiency, which is considered as one of the grand challenge in building control and thermal comfort field as well. So we started to review, as a part of NX79 subtask 4, we started to review OCC studies. So using the keyword searching, we found that there are more than 120 papers or OCC studies But in fact, there are only 42 field implementations in actual building systems, which indicates that there are some practicability issue when we apply OCC into actual building. So that requires some easily deployable or some doable OCC algorithms in actual building systems. Among those 42 studies, 23 occupancy-based controls, which are identifying occupants' presence or counting the number of occupants and using those information for whole building systems control. And there are also 19 occupant behavior-based controls, which are identifying the different preferences level or occupant behavior pattern and using those knowledge to identify the adaptive and personalized set point. So among those 19, 13 are direct sensing on occupant comfort, which are using biological sensing or app-based asking questions about the comfort. And 6 are indirect sensing, which are just observing how people use their thermostat or light switches and analyzing those diurnal pattern, identifying the comfort boundary of each individual people. So the study 1 is related to occupancy-based control. The name is a CRC-OOD. I'll detail the name later on, but I want to point out that this is a direct quote from NX79 subtask 2. So I'm going to applying advanced data analytics on existing data sources to develop or to identify the fundamental knowledge between occupants and their mobile devices, which can be used for occupancy-based control. Study 2 is RL-OCC, reinforcement learning-based occupant behavior-centric controls. And in this study, this is also direct quote from NX79, subtask 4. I'm going to tackle or develop some building operations strategies using online learning method to adapt the occupants to provide comfortable environment using less energy. So here's the contributions of this dissertation. The first CRC-OOD is basically capture and recapture based opportunistic occupancy detection. So try to build a simple and accurate detection system using existing data sources, which is IT infrastructure in buildings, and infer the number of occupants with minimal ground truth information and identify the fundamental relationship between occupants and their mobile devices. And the second one is RL-OCC, reinforcement learning-based occupant behavior-centric controls. Try to harness the complex dynamics of human building interactions by observing the diurnal patterns of people using their building systems. And it is online learning to adapt building systems to human continuously. And ultimately, it will balance occupant comfort and energy saving efficiently. So here's some graphical abstract of my studies of CRC-OOD and RL-OCC. So RL-OCC, as I mentioned, using the IT infrastructure to identify the fundamental relationship of occupants and their mobile devices using capture and recapture technique, and it's for more building level, whole building level analysis. On the other hand, RL-OCC is for more closed office unit, individual people, try to understand their preferences or behavior, and linked to lighting control or HVAC control, also linked to BAS system using reinforcement learning technique. So the CRC-OOD, it is just reiterating my previous sentence. And so researchers these days using opportunistic occupants detection, which means using the existing data sources to infer occupancy or occupant counts. That is because we have people carrying the Wi-Fi or Bluetooth devices for their daily life pattern, and we have IT infrastructure to use that. But there is a missing link behind this opportunistic occupancy detection. That is, most of models that researchers propose in occupancy-based control requires the Y label, which is number of people, to train the model in a supervised learning fashion. But to get this Y label data, that requires some camera installation to count the number of people, which have some privacy issue and expensive, and it's not doable for all buildings. And it's also labor intensive by manual counting. And as time goes by, people have to recalibrate those white label number of people to train their model again and again. So instead, I was trying to infer the more fundamental relationship between people and their mobile devices, which is R here, and mobile and N people. So here I introduce one interesting method from geology. So when geologists try to estimate the total population size of certain rabbit or certain species on this area, they use the capture and recapture estimator. It is an established method from very long history. And so one guy in the tent and count the number of rabbits and mark their ears, and they release those rabbits on day 1. On day 2, they capture new rabbits, and among them, 3 of them are actually recaptured from day 1. So by analyzing those patterns of capture and recapture and new capture, MCR, we can estimate the total number of rabbits from the geology perspective. Then we apply this technique to building domain, especially for Wi-Fi devices and mobile devices. So day 1, we capture 3 mobile devices and store their MAC addresses. So MAC address here means the unique identifier of each device. And day 2, we got 2 new devices, and just the one device was actually recaptured from day 1. So if day goes by, day N, we can have this generalized format, which is a Schneider index, to infer the total number of mobile devices in this building. And if we can divide this number by whole registered people in certain building, then we can infer the RCRC, which is the ratio that we want to identify. So we apply this CRC-OOD in buildings, actual buildings. This is ECJ building, home of CAE department, about like 1,300 people registered. So this is 100 days of MCR patterns. And applying our technique, we identify 1.42 Wi-Fi devices per person. We also apply this technique to other buildings as well. So as you can see here, every building has a different story in terms of the patterns of MCR. So that pattern also resulting in different R values. So that means we cannot use simple R value for every building, because every building has containing different different people, different population, and their population has different ratio of mobile devices. And CRC-OOD can adaptively learn different R values based on just IT infrastructure data. But one thing in my mind was it is limited to evaluate those numbers using ground truth data. So we used some simulation. We evaluate CRC-OOD on simulated environment. So in this case, there are 1,000 people, and we changed the R ratio, which is the ratio between people and mobile devices, from 0 to 3. So, and compare with the baseline scenario. So baseline scenario here means just count the number of cumulative numbers of the mobile devices and using it as a max number. And x-axis is the input numbers for the simulation cases, and y-axis is the results, the estimation results from both CRC and baseline method. Just only using 2 days of CRC, the results on CRC is very close to y equal x line, which is way better than baseline in terms of RMS rate as well. So this is 2 days of CRC and 7 days of CRC, getting close to y equal x line, 12 days of CRC, and 17 days of CRC. So after just 1 week of CRC, the RMS rate of CRC-OOD is very small. And baseline method requires almost 1 month to achieve the same accuracy as CRC method. So here's a summary of CRC-OOD method or CRC-OOD study. We identify the fundamental relationship between occupants and their mobile devices, which simply assumed in other studies. We use the CRC technique to identify that. And it adaptively calculates different ratios for different environments. And it uses existing IT infrastructure for large buildings with the minimum ground truth information. And it's easily applicable just using IT infrastructure to be a system, and it can be used for demand-driven controls. So this is about my first study, CRC-OOD. In the second study, I want to reiterate my review result here. And as I mentioned earlier, there are 19 behavior-based control, and 13 of them are direct sensing, and 6 of them are indirect sensing. So I want to focus on those 6 indirect sensing methods, which use analyze the diurnal patterns of how people use their building systems. For example, how they use the light switches or the thermostat, and just using online learning method on those data set and try to build the OCC operation strategies to provide a comfortable environment using less energy. And the first study I want to present here is a LightLearn, which is RL-OCC for lighting control. As a learning component, I would like to introduce, and I would like to introduce reinforcement learning. So reinforcement learning is formalized by Markov decision processes, and that is agent do an action to environment and get a state and reward, and keep try and error via interaction, keep iterating this loop, then agent will adapt to the environment. The one great example for RL is AlphaGo. So the Google DeepMind AlphaGo agent have no prior knowledge about the game of Go, but it just play with other human, and finally it learns the rule and won the human champion. Now, as I mentioned earlier, the core part of reinforcement learning is Markov decision processes. So I would like to spend some time to explain what MDP is. So let's assume that you have your car and you want to maintain your car in a good shape with the minimal cost. So you can define the car state as good shape, bad shape, and broken. Then you can have actions given that state. Either go to the maintenance shop or just ignore your state. So each action given state have some reward function. Here is spending some money. So if you're in good shape car, if you go to maintenance shop, you have to spend some money. But if you ignore that, you don't have to spend any money. But if your car is broken, and if you go to a maintenance shop or repair shop, then you have to spend more money compared to the good shape, go to the maintenance shop. So those are reward function. And there's a transition function between state, action, and next state. That is basically the probability between state to state given an action. So what RL agent should do in this problem setting was try to finding out the policy, follow the policy that maintain your car in a good shape with the minimal cost. The cost here is a value function, so which is an expected future reward. So what we have to do when we use this MDP technique in building system is we need to define state, action, reward, and transition probability and solve this MDP. So here's one example, which is LightLearn, RL-based OCC for lighting. So people use their light switches as usual, and the LightLearn learn adaptively adaptive set points for each individual and save energy consumption. So the left side, here's a photo of this LightLearn study. We used the Raspberry Pi Zero and the TSA2561 illuminance sensor and used the ready-made stuff SwitchMate to control over the classical switch. And to communicate everything all together, we developed some PCB board. So again, we have to define state, action, and reward for this LightLearn study. For the state action space design, we first consider the occupancy of the room. So by tracking the Bluetooth signal of the room, by asking their Bluetooth MAC addresses. So now the room can be divided into occupied or non-occupied. Then the second consideration is a switch position. So it's on or off. And third consideration is indoor light levels. It is from the occupant's perspective, it's a dark, comfort, bright. So having combination of those three factors, we can divide our room as 7 different episodic states. The last consideration is a period of day, which is increasing daylight period, midday, decreasing daylight period, and no daylight at all. So we can now describe our one day with 26 different episodic states so that we can calculate the transition probability between 26 states and avoid the causal dimensionality in this control problem. And we assign the reward for those episodic states for negative penalty term in when occupants in a discomfort or energy wasting situation, or neutral 0 for energy consumption for comfort, and positive reward for occupant comfort and energy saving situation. The last component here is we have to come up with the knowledge that LightLearn can need to operate. So once we gather the data related to state, action, reward, and every midnight, the LightLearn agent calculates the control law using value iteration method, which is part of dynamic programming, until the good policy enough. So policy here means a control law for the LightLearn operation. So here's an example how LightLearn works during the day. So there's a physical room environment. This physical room environment can be defined by occupancy, switch position, and indoor light level. And there's a cyber system that how the LightLearn understands this physical environment. So as I mentioned earlier, that there are 26 different episodic states, but here I just show the 7 different states, and LightLearn values each state by the value functions. So S13 is considered as negative minus 0.9 value, and S15 state is considered as 1.1 positive value. So this is a cyber-physical system of LightLearn operation. So here's a control operation example. So at 9:48, occupants enter the room, and it was a bright enough condition, so it enters the S15 state. The value was a max value, so the LightLearn doesn't need to do anything. And occupant left the room again at 10:27, and re-entered the room again at 10:39. And LightLearn understands that situation as S14 states. So given S14 state, what LightLearn can do is waiting for S15 state or turn on the light, go to the S17 state. But as S15 state has a higher value, so it's just waiting for the daylight condition. However, due to uncertainty outside the cloud cover, it goes to the dark condition, so it goes S13 state. So given that S13 state, what LightLearn can do is turning on light, go to S16 state, or just waiting for daylight outside, go to S14 state. But S16 state is slightly higher than S14, so it immediately turns on the light and go to S16 state. An occupant left the room at 12:39 without turning off the light, so it goes to S19 state, which has minus 0.9. So it immediately turning off the light, go to the S18 state, which is 0.98 value. So here's a whole that day operation. So LightLearn turn on or off to giving the occupants comfort situation and try to save energy. But from LightLearn's perspective, it is actually just finding out the optimal path for the maximum cumulative reward by playing just switching on or off game. We implement this study, this LightLearn study in actual building system. So this is again our home department ECJ building. The main question here is, does LightLearn save energy or learn adaptively different occupants? And how people think about this new technology? What is their perception of this new technology? So we choose 5 different offices, 5 different occupants intentionally, see how LightLearn can adaptively learn different things. So first, LightLearn can save energy compared to 2 other scenarios. One is a full operation, assuming that turning on light from 9 a.m. to 5 p.m., which is a worst case scenario. And the other is occupancy-based control, which is using the PIR data to, for example, using PIR to turn on the light when occupant occupy the room. So interestingly, LightLearn identified some energy saving potential compared to occupancy-based control. So here's some adaptiveness of LightLearn as well. So y-axis represents one of the control parameter, like threshold for darkness level, and 5 different offices. Until 10 days, it fluctuating a lot. Try to find out the right control parameter value. From 10 to 35 days, it more stabilized. From 35 to 50th day, like one occupant actually jumping and fluctuating a lot. That occupant was using the light switch after this 35 day, which indicates that LightLearn literally using the interaction data to learn its own control parameters. We also ask how people think about this LightLearn. So this is about like perspective. So they like some automations in their buildings, and they like some personalized agent try to learn for themselves. We also asked the dislike perspective of LightLearn, and majority of complaints were like automatic lights off action. So the main concern of people was they didn't know why lights off automatic action happened. That is because, but we intentionally choose this way because we try to avoid the bias setting of our experiment. So we didn't explain anything about our LightLearn operation, but people might think somebody taking off their opportunity to lighting on or off. So one future research direction from this problem or this finding is how much information we have to open or how to interact between occupants and their building systems. How smart building agent using interface device to explain about the control action decisions. So one example is a building avatar to explain everything, or the other example is just LED signal, like now you save energy and your light level, even though I turning off the light, your light level is enough based on your historical data set, something like that. So next question is, we want to know what if we install this device in different location or longer period. So we use the Python Energy Plus based simulation to test the generalizability of LightLearn operation, generating various occupant behavior agents. So we model the typical closed office unit in United States and generate some different OB agents using different occupancy schedule and lighting preferences. So first 50 days, it fluctuating a lot. Same control parameters that I explained before. From 50 to 100 days, this control parameter is trying is slightly increasing. And after 100 days until the end of the simulation, it shows smooth curvature for every offices. That means the LightLearn adaptive to the daylight variation in the indoor environment. So the next thing is applying RL-OCC for HVAC-Learn system. So here's the HVAC-Learn. So in this case, we're more focusing on how to integrate this RL-OCC with facility managers and using the BS data. And same, we use the reinforcement learning technique to tackle this problem. So similarly, we track the thermal environment, for example, indoor air temperature and humidity level, and how people use their thermostat or how people use their switch box I just showed, and using those data to updating the new set point for the building systems. And we plan to test this algorithm in one of the building in UT Austin campus. But when we discussed this project with the facility managers group, one of the concern from their perspective is they want to know everyone's preference level, but they have, given that there are more than 100 buildings in UT Austin campus, and each building has more than 100 people. So it is almost impossible to know or impossible to understand each individual's preference level efficiently. So by just complaint logs. So what we proposed to them was we build a human building interaction devices, this small switch box, HVAC-Learn, and then try to learn occupant behavior and patterns of their interactions and assist the facility managers to understand occupants more efficiently and robustly. And ultimately, this will balance occupant comfort and energy efficiency as well. So this is a literally human in the loop approach, not only occupant themselves, but also the facility managers group in our campus. Because the researcher who study, like me, who study AI for building systems, we have to put facility managers inside this loop because they are the most knowledgeable people who understand building systems. They might do some quality check beforehand. So full automation by using AI is not ideal solution, but we have to, the AI should be the assistant tool for facility managers for this OCC problem setting. So again, we have to define state action reward for this problem as well. One primary assumption we made here is occupants indicate their discomfort, either push those two buttons, too hot and too cold, or change their thermostats. So we monitor indoor air temperature when they press buttons or when they change their thermostats. First thing is a state reading of the previous day. So we analyze the distribution of indoor air temperature when people press the button. So the bottom figure represents this person pushed the button, too cold button around 20 degrees C and too hot button around 25 degrees C. And then using those T cold and T hot temperatures, which is cumulative learning throughout the experimental period, we identified certain days state as cold, neutral, hot. So if the occupant was occupied the room majority of their time less than T cold, then that day state was the cold state. And in between T cold and T hot, and it's a neutral, and it's hotter than T hot, then it's a hot state. The next thing is action selection. So for the action selection, we apply the T hot temperature for cooling set point and T cold temperature for the heating set point. But one thing we have to keep in mind is if we increase the cooling set point and decrease the heating set point, we'll have some energy saving potential by increasing that deadband. And if we decrease the deadband, then there will be better comfort potential. So that is why we consider T hot minus 1, T cold minus 1, and T cold plus 1, and T hot plus 1 as our action selections. Given 3 actions and 3 states, we now have 9 different Q values for each state, for each controller. So the controller select the max Q value action given previous state at every midnight. And to have some exploration opportunity, we select the random action with a low probability value, which we use the 5% in this scenario. And the third thing is a reward calculation. So reward here means how many times people push their too hot or too cold button. But we put some scaling factor, which is EF. And again, if it increases the deadband of the cooling set point and heating set point, then we scale it down less than 1 to attenuate those number of button presses. And other actions are just EF is considered as a 1. And the fourth step is update the Q values based on the reward value that they received. And we iterate this 1 to 4 steps every midnight, every daily pattern to try to adaptive Q values for different people and different indoor environment. Our plan was like 20 experimental group and 20 control group, and we actually installed these devices, and it was planned to long-term study for spring and summer 2020, and integration of HVAC-Learn to BAS and FM. But due to COVID situation and shelter-in-place order, we cannot get like enough data for this control. So instead, we try to simulate HVAC-Learn performance using Energy Plus. So in this case, we script the HVAC-Learn algorithm using energy management system in Energy Plus, and also script 2 different occupant behavior models. One is occupancy and the other is a thermal vote. So occupancy here means the binary numbers of 0 or 1 occupied or room is unoccupied for the closed office unit. And thermal vote is the probability of button presses or change the thermostat given indoor air temperature. We simulate this HVAC-Learn approach in typical office in Chicago, Illinois. And here's the results compared to reference control. So reference control here means the static set point, which is 20 to 25 in their heating and cooling set point. So you can see HVAC-Learn, the daily discomfort hour is a lot less than a reference control, but cooling energy is slightly less or almost same. And there's a too hot number of button presses for every month. So as you can see here, every month it shows a less button presses, but interesting pattern here is that it kept increasing until September. The reason here is because it learned the knowledge from the experience during the summer season. So HVAC-Learn choose the more conservative on their cooling control setting. So that's why it increased more to hot button, even it's in Chicago temperature. On the other hand, the heating control, the discomfort hour is almost identical, but heating energy is a lot less. It's less than that. And there's a too cold button, same here. As you can see here, there are almost double numbers of too cold button presses during the January and February. But at the end of year, November and December, it's almost doubled down. So this indicates that the HVAC-Learn agent was without no prior knowledge. It just online learning through the whole year. And finally, it continuously learned the right strategy to control this room environment. On the other hand, the January and February is more like an exploration period to get its knowledge. So for the further study, we can change the learning rate or learning time. So differentiating just observing period and controlling period. In that way, we can avoid the 2 problems that we identify for too cold and too hot situations. So here's a summary of RL-OCC. So as you can see, humans are active and passive agent in buildings. And human-building interaction determine comfort and energy system efficiency. And RL-OCC efficiently balance occupant comfort and energy efficiency. And reinforcement learning specifically learns different occupants in indoor environment. So to conclude, let's back to my original statement. We have problem related to energy and comfort. And I propose that OCC can be a viable solution to tackle this problem. Especially CRC-OOD can identify the fundamental knowledge of occupant and mobile devices. And RL-OCC can efficiently balance between occupant comfort and energy efficiency. And both are actually aimed at people, which is occupant-centric approach. And they are using existing data sources or new data sources or minimum installation of data sources and advanced analytic like capture and recapture and reinforcement learning and applying to individual building control and whole building control system as well. This is my first author publications during my PhD studies. I would like to thank all my co-authors for their support and the reviewers from journal articles and the conference paper, and all the audiences from my conference travel for their informative feedback. And I also thank my advisor and committee members and my lab members in IEL and all the support from UT Austin and including Green Fee Fund and the informative feedback and from the NX79 as well. Thank you very much.